Hello everyone, this is Team NeuroSymbolic and we're going to be presenting our idea of NeuroSymbolic Hypothesis Engine. So we are motivated by a persistent gap in material science where high throughput experiments generate vast, noisy data sets, but discovery still remains bottlenecked by human intuition and brittle heuristics. We set out to reimagine autonomous scientific reasoning. So our inspiration came from two fronts: from material science, the dynamic complexity of phase diagrams, the emergent metastable structures in the intractable combinatrix of dopants and synthesis pathways. And from the AI side, we took the inspiration that of recent papers on energy-based transformers for probabilistic reasoning, liquid neural networks, work done by MIT. Based on that, we were able to infer about dynamic memory, quantum inspired symbolic architectures which exist, which kind of work at the intersection of trying to fuse in the quantum mechanics ideas into machine learning, and then the contrastive learning grounded, which helps us in truly setting things up by following the laws of physics. So from this convergence, we emerged with the idea of neurosymbolic hypothesis engine, which is, to our knowledge, the first architecture to unify these sections or components together in an end-to-end real-time reasoning system, which is built for the purpose of materials discovery and hypothesis generation. NSHE represents a paradigm shift. It's not a predictor of materials, but a AI workflow and system that reasons them. So we have four key components. One is the energy-based system. So in that, we are using the continuous plausibility scores to candidate relations. We are also using the embedding symbolic constraints into inference, and using this, we're able to avoid any brittle or overconfident predictions from our system. Using the liquid neural networks ideas, we are able to model evolving phase spaces using ODE driven states, allowing dynamic updates with new synthesis or simulation data. The quantum inspired symbolic reasoner helps us in exploring hypotheses in parallel via the Hilbert space superposition, enabling discovery of rare, non obvious material behaviors. And the contrastive embedding alignment helps us in grounding these latent representations in formal physical constraints, symmetry rules, valence, electronegativity rather than data correlations. So while each component has existed in isolation before in many of the papers, but the energy-based models or the symbolic engines, the contrastive learning liquid networks, but our architecture is the first to fuse them together into a differentiable, tightly coupled pipeline for autonomous scientific hypothesis generation. Compared to prior neurosymbolic approaches like deep probe log, logic tensor networks, or LLM based hybrids, our method offers dynamic adaptability. Using these components, we're able to also help physically grounded inference and also traceable hypothesis generation. The simple motivation at the end of the day was not to just generate another black box predictor, but we wanted a system that was able to think, one that uncovers causality, not just correlation. And from that need and the profound complexity of material science, this idea of NSHE was born. So in this GitHub, you can see we have detailed the core components that we've used, and also the key innovations according to our pipeline, and the impact and the vision with which we came about with this idea. And again, like, our idea is not free of any kind of limitations. There are large limitations because of the data set issues, as well as the we've been largely been using the open source models because we wanted to keep it reproducible and available for most of the people out there. And this is basically the pipeline design that we have got. If you look, as part of our code files, we have generated the notebooks which can be looked at, and we also have generated a CSV which gives us better understanding of how we're performing against the rule-based systems, as well as similar sized open source models, what they are doing, what components we have added out that is helping us in getting the gains that we are seeing. And yeah, so that's pretty much it. This idea was born from the inspiration to unify various architectures together and see how we can use all of them and make a much more better system that's capable of better hypothesis generation by taking into account the different ideas that come behind and these kind of architectural implementations. Thank you.